This video is for Chemistry in the Earth System, Unit 1.1, Heat. Today's essential question is, what is heat and how is it transferred? Hello, baby birds! Today we are diving into an essential question that helps us understand one of the most important concepts in all of physical science. What is heat and how is it transferred? Our focus will be on three main mechanisms of heat transfer. They are conduction, convection, and radiation, as well as how these relate to the conservation of energy. As a fun and relevant example, we'll return often to the lava bread from Iceland idea. In Iceland, people use geothermal heat, naturally occurring heat from the inside of the earth, to bake bread underground. That process involves all three methods of heat transfer, and we'll unpack how it works scientifically as we explore these concepts. So let's begin with the definition of heat. Heat is the transfer of thermal energy from a substance at a higher temperature to one at a lower temperature. It's important to understand that matter does not contain heat. Instead, heat is energy that is in motion. This energy continues to flow until the two objects, which are in contact, reach the same temperature. This balanced state is called thermal equilibrium. In the lava bread example, the hot geothermal ground serves as the high temperature source, and the dough is the low temperature object. Over time, heat flows from the ground into the dough until both reach similar temperatures, allowing the bread to cook evenly underground. A key misunderstanding that we need to clear up is the difference between heat and temperature. Remember, like we just noted, heat is the transfer of energy due to a temperature difference. It's measured in joules or calories. Temperature, on the other hand, is a measure of the average kinetic energy of the particles in that substance. It tells us how fast the particles are moving, and it is measured in degrees Celsius, degrees Fahrenheit, or Kelvin. Here's a practical comparison. Imagine a large cup of hot water and a small cup of hot water. Both are at the same temperature. Even though they have the same temperature, the large cup contains more water molecules and thus more total thermal energy. It holds more heat. This is because heat depends on the amount of energy in motion, while temperature is just a measure of the average. Now, many people believe that heat and temperature are interchangeable, but they are not. Another common misconception is about the direction of heat flow. Heat always moves from areas of higher temperature to areas of lower temperature. There is no natural process in which heat flows from cold to hot, unless additional energy is applied, which is the case in the example of a refrigerator, which uses electrical energy to move heat from a cool interior to the warmer outer room. Some also believe, mistakenly, that insulation keeps cold out. But what it actually does is reduce the loss of thermal energy from inside to the outside. Back to our lava bread example, some insulation is used to prevent too much heat from escaping the ground before it cooks the bread. This ensures that the bread receives a consistent and sufficient amount of heat from the surrounding earth. Now let's connect heat transfer to the law of conservation of energy. This law states that energy cannot be created or destroyed. It can only be transformed or transferred. In an isolated system, in which no energy or matter can enter or leave, the total energy remains constant. If one part of the system, just one part of the system, gains thermal energy, another part must lose an equal amount of energy. For example, In our lava bread scenario, when the dough absorbs thermal energy from the ground, the surrounding earth cools slightly in response. Even in large industrial settings, this principle holds. Excess thermal energy, which we sometimes call heat waste or waste heat, this can be captured and used to generate electricity through steam turbines or to heat nearby buildings. Factories and power plants generate large amounts of waste heat. Instead of letting this energy go to waste, we can convert it into other useful forms. One method is to use it to boil water and have that boiling water drive steam turbines that in turn generate electricity. Another method is to use it directly for heating through a process called district heating, where hot water is pumped through pipes into homes and surrounding buildings. These processes are examples of how understanding heat transfer allows us to use energy more efficiently, just like how Icelanders make use of geothermal energy to bake bread without using electricity or gas. To fully understand how energy moves, we also need to understand the types of systems that exist in our physical world. First, we have open systems. Open systems can exchange both energy and matter with their surroundings. Closed systems can exchange energy, but not matter. And in isolated systems, there is no exchange, either of energy nor matter. The Earth, for example, is considered a mostly closed system because it exchanges energy, like sunlight, but not matter into space. In the lava bread example, the underground cooking site functions like a closed system. It allows thermal energy to transfer from the hot rock or ground into the dough. But the matter, which is the bread and the ground, stay in place. Heat can be transferred in three ways. Firstly, conduction is heat transfer through direct contact, often in solids. Then there's convection, which is a heat transfer through the movement of fluids. And just a quick aside, fluids include both liquids and gases. And then there's radiation, which is a heat transfer through electromagnetic waves, which can occur even in a vacuum. All three methods are in play in many real-world situations, including baking bread underground. The ground conducts heat into the container. Air pockets may circulate through convection. And if the dough is near a hot surface, it might absorb some radiant heat as well. Conduction occurs when thermal energy is transferred from one particle to another through collisions. When one part of a solid, like a metal rod or a baking container, is heated, the particles in that region move faster and they collide with nearby particles, passing on that thermal energy. Eventually, this process spreads heat throughout the material. And in solids, where atoms and molecules are closely packed, conduction is very effective. This is why the outer shell of a bread container becomes hot when buried in the ground in Iceland. Materials vary in how well they conduct heat. Metals such as copper and iron are excellent conductors because they have free electrons that help transfer energy quickly. These are used in cookware and heat exchangers. On the other hand, materials like wood, paper, plastic, and fiberglass are poor conductors, making them good insulators. These materials resist heat transfer and are often used to control energy flow. Insulating materials are often included in lava bread preparations in order to prevent the outer earth from overcooking or drying out their dough. Convection takes place in fluids. Remember, that includes both liquids and gases. When a fluid is heated, its particles gain energy, therefore spread apart, and become less dense. The warmer, now lighter fluid rises, while cooler, more dense fluid sinks. This creates a circular motion called a convection current. In the underground lava bread chambers, Warm air or steam may rise from the deeper areas, heating the dough through multiple angles. This same mechanism explains how room heaters work and how ocean currents and wind patterns distribute heat on a global scale. Now, let's explore a few real-world examples of convection. In home heating, hot air from heaters rises to the ceiling while cooler air descends so that it can be reheated. In the ocean, cold water near the poles sinks, while warmer waters, which are typically near the equator, rise and move along the surface. In the atmosphere, the sun warms the Earth's surface, causing warm air to rise and cooler air to replace it, which results in wind. These natural and engineered processes rely on the movement of fluids to transfer heat efficiently. Radiation is the transfer of energy via electromagnetic waves. It doesn't require a medium, which means it can happen even in a vacuum like space. The most familiar example is sunlight, which travels through space to warm the Earth. All objects above absolute zero, which is the coldest temperature that can exist, emit some form of radiation. The hotter the object, the shorter the wavelength of the radiation that it emits. In the lava bread example, if hot rocks or air surfaces are exposed, they emit infrared radiation, which can also help warm the bread surface. Some common examples of radiation include, but are not limited to, sunlight warming your skin, fires giving off heat so you can feel warm from a distance, microwaves heating your food, or thermal cameras detecting infrared radiation from warm bodies. Radiation works over distances and doesn't need direct contact or fluid movement, which makes it different from conduction and convection. Now, let's compare these methods. Conduction requires matter and involves direct particle collisions, examples being touching a hot pan or heating a spoon. Convection occurs in fluids and involves movement of heated particles, examples being boiling water, ocean currents, and air circulation. Radiation does not require matter and uses electromagnetic waves, examples being sunlight or heat from a campfire. In lava bread baking, heat moves from rock to dough by conduction, circulates through underground air via convection, and radiates from hot surfaces onto the dough. Engineers and scientists apply these concepts to some real-world problems. So, to slow heat loss, we use insulators. To transfer heat efficiently, we use conductors. In experimental activities, students like you can compare materials to see which best prevents heat loss, just like engineers test insulation for airplanes or houses. In Iceland, choosing the right materials to wrap or bury bread helps ensure optimal cooking conditions. Now, understanding heat transfer lets us design better buildings, more efficient machines, and even improve cooking methods. Whether it's using radiant barriers in homes, convection ovens in kitchens, or metal cookware for fast conduction, the principles stay the same. Geothermal systems for heating homes use Earth's internal heat, just like in our lava bread example. These applications help conserve energy, reduce costs, and protect the environment. So, to summarize, heat is the transfer of energy due to a temperature difference. It's not stored, it's always in motion. Temperature measures the average energy of particles. Conduction, convection, and radiation are the three primary ways heat is transferred. The law of conservation of energy tells us energy isn't created or destroyed, it's just moved or transformed. And finally, real-world events like baking lava bread in Iceland give us vivid, tangible ways to understand and apply these scientific principles. At this point, you should be able to generate a full and appropriate response to today's essential question: what is heat and how is it transferred?